Hello there, and welcome back. In this video, we're going to continue our discussion of statistics, but shift our view from one-dimensional data to two-dimensional data, and you can of course extend this to three or higher dimensional data if you wish, by using similar or maybe the same principles. So a two-variable numerical data set consists of a bunch of points where the points consist of two values, where the first value x can represent temperature and the second value of x can represent something else such as pressure or volume. So what you can do is you can measure the temperature and pressure at a variety of different times, for example time 1, 2, 3, 4, and so on, and that can construct your two-variable numerical data set. Since it's two variables, one of the easiest representations graphically is to construct a scatter plot of those particular points, and that can give you some idea of what's going on between your data points. So one of the very first natural questions that one can ask, at least in this narrative of statistics, is are there measures of central tendency, position, and standard deviation for two-dimensional data sets? And of course the answer is going to be yes. So the very first, that measures word looks a little sloppy, let's just fix that. So measures of central tendency, position, and standard deviation. So for example, measures of central tendency, we can do the mean of x comma the mean of y, right? So it's going to also be a two-dimensional metric. And of course this is going to be an approximation for mu x comma mu y, the population mean values of x comma the population mean values of y. So that's the 2D arithmetic mean. We could do the median of x comma the median of y, which would be an approximation for the population median of x comma the population median of y. And then we could also do, for the measures of variation, we could do the standard deviation of x comma the standard deviation of y, which would of course be an approximation for sigma x comma sigma y. So those will be the two-dimensional means, two-dimensional medians, and two-dimensional standard deviations, which are, some of the basic measures of central tendency, position, standard deviation that we have that is commonly used. So those are some of the metrics that we can define, and we can interpret them in very similar ways as we did with the one-dimensional case. So let's start talking about some questions that are natural that we ask about two-dimensional sets that we usually don't answer or ask about one-dimensional data sets. So the very first one is this: does there appear to be a correlation between all of the x values, which I'm going to call capital X, and all of the y values, which I'm going to call capital Y? Now, what do I mean by correlation? So usually what people mean by correlation is, as you increase one variable, some people call it the independent variable, what happens to the other dependent variable y? Does it increase, decrease? Does it have some pattern associated to it? The easiest correlation that we usually study would of course be a linear correlation. So of course as one increases, the other will increase or decrease or do something like that. But this is not the only type of correlation that one could have. For example, one could have a parabolic correlation, one could have an exponential correlation, one could have a logarithmic correlation, one could have a sinusoidal increasing correlation, one could have a variety of different correlations. As to how to measure each of those things is a completely different story, but a very good starting point is a linear correlation between x and y, because at least then you can approximate the correlation between the other types of correlations on, for example, subintervals of the entire data set. So with that in mind, let's just go into linear correlation in a little bit more detail. So let's just draw a couple graphs of some types of data values. So if you see your data set looking like this, where you sort of see like a positive line sort of going through there in your minds. So this is what we usually refer to as a positive correlation between x and y. But of course it doesn't have to look like that. It can look in the opposite way. For example, the data points can sort of have a downwards trend. So you can sort of imagine a little line going down there, so that would refer to as a negative correlation. Or your data values could look something like that, right? A bunch of scattered points. And you look at that, you're like, well, I don't really see any point or pattern there, so I would say that there is no correlation between x and y in that particular case. Now, keep in mind, these observations are indeed qualitative observations. There's nothing mathematical, well, maybe there is, about these observations. Um, and that's really a problem because some people can look at these data points and maybe see a pattern that other people cannot see. And then people would argue and it would cause confusion and stuff like that. That's why we create these metrics that people can communicate with. And everyone can sort of understand what people are talking about. So that's the goal of communication, right? So one of the very easiest ways to measure, so how to measure linear correlation. So what is a metric to measure linear correlation, especially in 2 dimensions? And the answer to that question, the first metric, or the first of a couple metrics that we're going to investigate, will be the covariance. The covariance of a data set. So the covariance, and I'm going to define it for the population and the sample so you can see the difference between the two. So the covariance, which I'm going to abbreviate by COVP, so that's the covariance of a population, so this is going to be a parameter, is going to be equal to the sum from k is equal to 1 to the population size. So what is the population size in this sense? That's the set of all possible points that you could gather. And that's going to be the value xk minus the mean of x times the value yk minus the mean of y values, all divided by the population size, capital N. And for the sample covariance, so COVS, not cos, COV, this is going to be equal to the sum from k is equal to 1 to little n, that's the sample size, xk minus x bar times yk minus y bar, all divided by n minus 1, so the same difference as was, for example, the sample and population standard deviation and variance formulas. Population is divided by n, and sample is little m minus 1. So of course this formula should look very similar to the variance formula in 1 dimension, except the xk minus mu x term squared is decomposed into x and y. So it's practically the same exact thing. So since it looks a little bit complicated, let's just go through a little numerical example to sort of show you how to use this formula to calculate the covariance of a sample. So let's look at this particular example that consists of 3 particular data points. So this point, and that point. Sometimes it might be easy to put the x values in one particular set and the y values in another particular set. For example, the x values is going to be consisting of 5, 7, and 9, and the y values are going to be consistent of the values -3, 4, and -4. And it's easy and it's important to remember the association between these numbers because you cannot mix them up for the covariance calculation. But from these individual sets, we can actually calculate a few metrics that are actually going to be used for these two-dimensional metrics, in particular the mean and the standard deviation of each of them. So I leave it as just a little exercise for you because this is something we did before, that the sample mean for this particular data set X is going to be 7, and the standard deviation for this particular data set is going to be equal to 2, and the sample mean for this particular data set Y is going to be equal to -1, and the standard deviation for Y for this particular data set Y is going to be equal to the square root of 19. I'm just going to keep it in exact form so I don't have any round off errors. So what can I do with these numbers? So the first thing I'm going to do is I'm going to calculate the covariance of my data set S. So what I'm going to do is I'm going to take the value X minus the mean of X times the value Y minus the mean of Y and add all of those things up. So the very first value of X is going to be 5 minus its mean. Its associated Y value is going to be -3 minus -1. So that's going to be -3 plus 1. And then we're going to have 7 minus 7, and then 4 minus -1, and then plus 9 minus 7 times -4 minus -1, all over, and if this is a sample, then that's going to be 3 minus 1. So once we work that out, That's going to be equal to negative 2 divided by 2, which is going to come out to negative 1. So the very first thing that you should observe about this particular number is that this number can be less than 0, unlike the variance of S and the variance of a population, and also the standard deviation too, for real numbers at least. So the covariance can be a negative number. So that's a little bit interesting, but it allows us to talk about, for example, negative correlation versus positive correlation. So it's actually a good exception compared to those two. Now let's talk about a couple properties for the covariance that are going to be useful in terms of its interpretation. So property 1 is that the covariance is an unbounded two-dimensional metric. So what does this word unbounded mean? So when I say unbounded, that means the covariance can be any number from minus infinity to positive infinity. So it could be 5, it could be 10, it could be negative 6.5, it could be 5 million, it could be negative 62,576,000,576. It could literally be any number. And why can that be an issue? Well, what if somebody says, well, this has a negative correlation? Do they mean negative 5? Do they mean negative 500? What do they mean by a negative correlation, or maybe even a strong negative correlation? Is that negative 5 million, negative 5 trillion? Like, how large needs to be large in order for you to consider it to be a large versus a weak correlation? So having an unbounded metric sometimes creates a little bit of an issue there. So that's one property of covariance, and it's not really a good one. Another property, also is not a good property, is that the unit typically does not make sense. The unit, so I mean like kilogram degrees Celsius, and so on like that. So for example, if I look at a particular example of a data set S, where the first data points are measured in centimeters, so all the x values are centimeters or lengths or something, and let's assume that the second unit, y, is measured in kilograms, so it's like weights or masses or something. So if that is the case, that means the covariance of S is going to come out to something like, I don't know, 543.121 centimeter kilograms multiplied together. So what's a kilogram centimeter or a centimeter kilogram? So this unit usually doesn't make sense. Now you can start assigning meaning to these units. That's of course true, but at least on the surface they do not have any natural, at least maybe, meaning to you compared to the centimeters and kilograms, the things you're measuring things in already. So that's another downside that is often associated to the covariance. So, but it does tell us linear correlation between data points, so it's not completely useless. So maybe we can create another metric that overcomes these two things and still preserves that correlation between two variables, that linear correlation that we really are trying to measure here. So the next measure of correlation that we're going to be using is going to be the correlation coefficient. Some people refer to this as the Pearson correlation coefficient, but I'm just going to refer to it as the correlation coefficient. So the correlation coefficient for a population, which is going to be represented by the Greek letter rho, sometimes it's used for density in chemistry and physics also. So some people will also write this as CORR, short for correlation of the population. This can be found by taking the covariance of the population and dividing by the product of the standard deviations sigma x and sigma y. Important note, these are standard deviations, not variances. So that is the parameter rho, the correlation coefficient of the population. And then we have the correlation coefficient for a sample, so CORR of S. So that's going to be equal to the covariance of S divided by the standard deviation of X times the standard deviation of Y, the sample standard deviations, of course. Right? And that's going to be the statistical estimate for the parameter rho. So if we continue our last example that we were doing, so I already told you what the standard deviations were, so that means you can easily find the variances. So what can we find? So if that is the case, then the correlation coefficient for that particular data set, which again is the covariance divided by the product of standard deviations. So this is going to be equal to negative 1 divided by 2 square roots of 19 if you just substitute those three things that I gave you before. And that's going to come out to approximately negative 0.1147. So now that we have this number, now I need to sort of convince you, well, why is this metric better than the other? So a couple properties of the correlation coefficient, R or rho, depending on what you're working with. The very first property is that the correlation coefficient always belongs to the closed interval negative 1 and 1. Therefore, it is impossible for you to have a correlation coefficient equal to 2, negative 1.3, negative 5 million, or anything outside of this closed and bounded interval. And this is for every data set. So if you're doing some calculations and you come out to a correlation coefficient of 1.3, you've made a mistake in your calculations. That's guaranteed. And another interesting property, if the absolute value of R or the absolute value of rho is equal to exactly 1, then the data set is perfectly linearly correlated. Either positive or negative, it doesn't matter. The absolute value, so that means it could be 1 or negative 1. 1 is going to correspond to your perfect positive linear, and negative 1 is going to correspond to your negative perfect linear. So now that we have a bounded and closed interval, now we can maybe assign some interpretations to all of these numbers, right? So let's draw a little scale. So go from negative 1 to 0 to positive 1. So as I just mentioned before, negative 1 corresponds to a perfect negative linear correlation, and positive 1 corresponds to a perfect positive linear correlation. And when I say perfect negative versus perfect positive, that means all of the data points directly fall in a line, either going down or directly going up. There's no skewness to the data points from the line. And let's draw a couple categories here. So this is going to correspond to a strong negative correlation. So let's draw a little data set there. So it's pretty much like that. So that's a strong negative correlation. And similar over here, this is going to be a strong positive linear correlation. So that's going to look similar to that. And let's draw a couple more categories here just to fill it out. Let's go here. So this is going to correspond to a weak negative correlation. So weak negative correlation sort of looks like that. And similarly for over here, this is going to be a weak positive correlation, so something like that. And then in the middle, that is the no correlation whatsoever. That's where you have practically randomness there. So those are all of the different categories for correlation coefficient interpretation. Now, an interesting point that you may want to investigate is, well, how do we define these points here? The cutoff between weak versus strong, right? So let's just, mention a little point there. So these cutoff points will depend on your study topic. So for example, those cutoffs should be closer to plus or minus 1 if you're working with something very sensitive, for example, medicine or something like that. But if you're looking at the correlation between ice cream and how much your dog, likes hanging out with you, maybe you'll put these thresholds a little bit closer to 0 because maybe it's not as a serious topic, or maybe it is and you can put it closer to 1. So those are some of the basic ideas associated to correlation. And there's one other type of metric that's commonly used. It's called R squared or rho squared. So that's just the square of the correlation coefficient. So this is referred to as the coefficient of determination. And all the coefficient of determination does, it's the same as R, but it disregards the direction of the correlation. So it tells you how strong is the linear correlation. So how strong is the linear correlation? But it doesn't answer, in which direction is it positive or negative linear correlation. So it only asks that question. So those are 3 of the metrics that are often used to calculate the correlation between two data or two variable data points. So what else can we do with this correlation thing? So the next thing we're going to look at is the line of best fit and some of the applications associated to that. So since we've been talking about the linear correlation between two-dimensional data points, it's natural to try and figure out, well, if there is a linear correlation between these data points, how would we find a line that would best model or best describe or maybe best approximate the data values that I've collected in my data set? And then maybe we can use something with this equation of this line. So remember that one of the representations for a line in terms of its equation is y is equal to mx plus b. To distinguish between the values y in our data set and the approximated points on our line in red, I'm going to be using y hat to represent the estimated value associated to some value x in our data set. So y hat is going to be a predicted value where y is going to be an obtained value. So what exactly is this line and how do we find it? So I'm actually going to zoom in on part of this picture and I'm going to look at a couple concepts that we're going to use to define this line of best fit. So this is our line here, and let's just draw a couple points. Let's assume that this is an actual y value. So this is going to be equal to x1 and this is going to be equal to y1. And that means if that is x1 and y1, that means this value right here, this is y hat 1. And then we can have another value over here if we want. For example, this is going to be x2. Let's assume that this right here is y2. So this right here is going to be y2. That means this value all the way up here, that's going to be y2 hat. Okay, so y2 hat. So remember, this value here is the obtained value. This value here is the predicted value. So this difference between the two is going to be known as a residual for a particular value of x. So in terms of a definition for the residual, so the residual for a particular value, xk, is going to be equal to the obtained value minus the predicted value. So obtained minus predicted value. So that's all a residual is. Obtained minus predicted. So what is another measure that we can use, or another metric to measure the strength of the linear correlation? Well, the coefficient of determination is a metric to measure the strength of linear correlation. Another measure that we can use to measure the strength of linear correlation is what we call the sum of squared residuals. The sum of squared residuals. Some people will just abbreviate that as SSR. So the sum of squared residuals for a particular data set S, and let's assume it's a sample, it's just going to be equal to the sum of all of the residuals squared. So yk minus yk hat squared. Or we could just rewrite this as the sum from k is equal 1 to n of the residuals squared. So how can we interpret this? So one thing, if all of our values lie on our line, so let's assume these are our data values, that means a line goes past through all of them. So this means that r is equal to 1. Notice if r is equal to 1, there's a perfect linear relationship between these data points. That means the distance between the values and the line is equal to 0 for all of the particular value points xk. So if r is equal to plus or minus 1, so this is actually an important property, if r is equal to plus or minus 1, then the sum of squared residuals for that particular value s is going to be equal to exactly 0. So if the sum of squared residuals is close to 0, that means the strength of the linear correlation is really high, right? So that's an important thing that you should keep in mind, and that's one of the reasons why the sum of squared residuals is a common metric for measuring the strength of the linear correlation. Now, what is this line of best fit? Like, how do we find the value of m and b? So the line of best fit And we can take this even as a definition. So the line of best fit for a two-dimensional data set S is the line in two-dimensional space R2 that minimizes the sum of squared residuals for that particular value data set S. Because clearly if we were to draw this line, clearly there's going to be residuals that is higher than the orange line, right? And similar can be said about the line that I drew before. So if the line of the best fit for S is a line in R2 that minimizes the sum of squared residuals for the data set S, then comes the natural question, so what are the values for M and B in the equation y equals mx plus b? So there is an analytical proof for this. Since we're dealing with minimization of a particular function, you're definitely going to have to use calculus for this. So I'm just going to give you these formulas out, but you can prove it if you are feeling adventurous. So the slope of the line of best fit is going to be equal to the covariance of the particular data set divided by the variance of x, variance of the independent variable. Important, it's not standard deviation, it is variance of the independent variable, x. Very important. And the y-intercept, or the vertical intercept rather, is going to be the average of y minus the slope that I just stated times the mean of x. So that is going to be the vertical intercept of b. So now we have formulas for calculating our slope and our y-intercept of the line of best fit. So now we can continue with our example that we were dealing with. So remember our data set was 5 minus 3, 7, 4, 9, minus 4, and we calculated several different things for it, right? So we calculated the covariance, and we calculated it to be -1, the mean was equal to 7, the mean of y was equal to -1, the standard deviation of x was equal to 2, the standard deviation of y was equal to square root of 19, so that's a little statistic summary, and from it we also said that r was equal to -1 over 2 square root of 19. Now important, if the correlation coefficient of a data set is negative, this means that the slope of the line of best fit will also be negative as well. Those are always going to match together. So if your data is positively correlated, that means the correlation coefficient will be positive, and the slope of the line of best fit should be positive as well. Those should always match. Now let's calculate the particular value of m and b. So that means m is going to be equal to the covariance divided by the variance of x. So the standard deviation of x is going to be 2, and once we square that, this is going to give us -1/4. And the y-intercept b is going to be y bar minus m x bar. So that's going to be equal to -1 plus 7 over 4, which is going to be 7 over 4 minus 1, which is going to be 7 minus 4 over 4, which is going to be equal to 3/4. So that is going to be the vertical intercept. That means the line of best fit, y hat, is going to be equal to m x plus b. So that is my slope-intercept form of my line of best fit. So since we have our line of best fit, now we can calculate the sum of squared residuals and interpret as necessary if we want to. So how do we calculate our sum of squared residuals? So we're going to make a table. So x, k, y, k is going to be our data elements. So that's going to be 5, 7, 9, -3, 4, -4. And then for our y, k hat, what we're going to do is we're going to take our y values and substitute them in for x, and that is going to give you our y hat k values, right? So if we subscript k, that is going to generate those values. So -3 times -1/4, and then add 3/4, that's going to give us -0.5. Do the same for 4, that's going to give you -1. Do the same for do the same for 7, that's going to give you -1. Do the same for 9, that's going to give us -1.5. Then I'm going to calculate my squared residuals. So my residual is going to be yk minus y hat k. Then I'm going to square it. So that's going to be -3 minus -0.5 squared. That's going to come out to 6.25. Then 4 minus -1 squared, that's obviously going to be 25. And then -4 minus -1.5 squared, that's going to come out to 6.25. So then I'm going to add up this particular column. So the sum of squared residuals for my particular data set is going to be equal to 37.5. Of course, the closer that is to 0, the stronger the linear correlation is. But you have to really understand your data set to understand, is this really close to 0 or not? And same thing can be said about the correlation coefficient that we calculated before. Like, is it really close to 1? Is it really close to 0? You really have to understand your data set to create those benchmarks to answer those questions. So one last thing to remember about these things. So just remember that y hat equals mx plus b is a statistic. It is a slope-intercept representation of a line associated to sample data. So that means this is an approximation for a line of best fit, y hat, with parameters beta 1x plus beta 0. So that is going to be the slope and the vertical intercept associated to the population line of best fit. So if that is the case, that means M is an approximation for beta 1 and B is an approximation for beta 0, right? So M and B are statistics, beta 1 and beta 0 are their corresponding parameters. And one last thing in terms of applications, let us assume you have your line of best fit. There's your data values. Let's assume that's going to be the minimum value of x, and that's going to be your maximum value of x. And let's extrapolate this data with some particular line. Right? Let's draw some vertical lines at the x minimum and x maximum. And how would you apply this to the real world? So if you take the line of best fit and, for example, you plug in a data value that you didn't have in your original dependent variable data set, any of those calculations are going to be referred to as extrapolation. Extrapolation. So let's just spell that out. Extrapolation. Right? So any approximation on data values that are located between the minimum and the maximum of the original data set, extrapolation. Then, if we want to go in the future, this would be a forecasting. Now keep in mind, we do not have any data in the future past the maximum value. So these values are not going to be reliable. Same thing can be said with backcasting. Some people refer to this as retrodiction, but forecasting backcasting are sort of backwards of each other. Again, we do not have any values over here, so that's not as reliable as, for example, the middle part, extrapolation. This is the most reliable approximations because we have data in the middle. Of course, the middle area, for example, the inner quartile area, is going to be more reliable compared to the outer quartile regions, but they're going to be more reliable compared to the values in the outlier extremes where we don't have any data at all. So those are just some of the very basics associated to two-dimensional data, linear regression, and also linear correlation for two-dimensional data sets. You can of course extend this to higher dimensional data if you wish, but that usually requires a little bit background in linear algebra to make it a little bit more efficient. So maybe in the future we'll talk about that, but for now, I'll see you in the next video. Take care.